Good morning, good evening, good afternoon. Happy Sunshine Day. It's trying to sunshine today. Now, today, guys, we start our leap from the submicroscopic world of individual atoms and molecules up to benchtop chemistry. What we're going to start doing now is we're going to start picking up the math of chemistry, the bookkeeping of chemistry that I skipped earlier. Okay? So we're going to go back and pick up parts of chapter 1, parts of chapter 4. We're going to pick up some things that we avoided as we discussed things in the world of the itty bitty. What we want to know now is, as we run things, reactions in the macro world, the world that we live in, and we tie it back into the submicroscopic world, we've got to be able to keep track of amounts of material, because we've got to obey the law of conservation of mass. Remember that during a chemical reaction, matter cannot be created or destroyed. Okay? So it doesn't matter if it's a physical process, it doesn't matter if it's a chemical process, we always have to obey the law of conservation of mass. So we're going to go back and pick up chapter 1, section 10, it's on page 57. What we need to be able to do here is we need to be able to scale up. We want to be able to count atoms, but we know realistically that we cannot do a direct count on our atoms. Okay? So we're going to need something that's going to be able to allow us to scale up. Our scale up tool is the mole. Okay? Now this is not a furry creature that plays in the dirt that's kind of black in color and semi-blind. The mole here is something totally different. We all know by now that all matter that we use in chemistry comes in hunks, okay? Atoms or molecules. And the atoms are very tiny. And if we want to measure out very tiny things, it's a little hard to do by direct count. So if you were in a paperclip factory or a sewing needle factory, and you got an order for 20,000 needles, and your paperclip factory got an order for 50,000 paperclips, it would be very costly to go out and send workers to your warehouse to count those directly. If we wanted to measure out something like that, we would count by weighing. And if we count by weighing, and I see a typo there, what we do is we figure out what the mass of one needle or one paper clip is, multiply by the number that I want, and then we weigh out that amount. Would we hit the exact number of needles or the exact number of paper clips we wanted? No. Would it be close enough? Heck yeah. And the person who is receiving it on the other end isn't going to count either. So we're going to count by weighing. Okay? Now, that's where the mole comes in. The mole is also referred to as the chemist's dozen. A mole is defined as the number of carbon atoms in exactly 12 grams. Exactly 12 grams of carbon-12. Remember, carbon-12 is an isotope of carbon. It has 6 protons and 6 neutrons. And it's the most common isotope of carbon. It's a very common atom. It's a very common isotope. It turns out in exactly 12 grams of carbon-12, there are 6.022 times 10 to the 23 atoms. So we can say that 1 mole is equal to 6.022 times 10 to the 23 items. Okay? 6.022 times 10 to the 23 is also referred to as Avogadro's number. Named after a scientist who butted heads with Dalton, and he was right, Dalton was wrong, but Dalton won the argument because of who he was. Okay? And we all know that that always falls out in the end. So 1 mole is 6.022 times 10 to the 23 items. 6.022 times 10 to the 23, Avogadro's number. So one of the things that we can say now is that if I'm given moles of A, then I can go to atoms of A by using Avogadro's number. 6.022 times 10 to the 23 atoms for 1 mole of atom A. Okay? So if we were to do a really simple problem, let's say that you had 2.5 moles of argon, and I wanted to know atoms of argon. Then all I have to do is go 2.5 moles of argon times 6.022 times 10 to the 23 atoms of argon for every 1 mole of argon. Okay? And I grab my handy dandy calculator, 2.5 times 6.022 exp23, and I get an answer of 1.5 times 10 to the 24 atoms of argon. Now I want you to notice here, okay, that moles and moles divide out. You can think about that 2.1 as being over 1, so that's in the numerator. Numerator and denominator, the units cancel out, and I'm left with units of atoms of argon. All right, not bad. Fairly easy and straightforward. We can also go the other direction. If I've got atoms of something, I can then say that 1 mole of whatever that is over 6.022 times 23 of whatever the item is gives me moles of that material. So let me show you a problem here. So let's say that we had .76 times 10 to the 23 atoms of neon. And I wanted to know how many moles of neon that was. Then 3.76 times 10 to the 23 atoms of neon. I'm going to go 1 mole of neon on top, 6.022 times 10 to the 23 atoms of neon on bottom. So notice that atoms of neon divide out. I'm left in moles of neon. So 3.76 exp23 divided by 6.022 exp23, and I get an answer, 3 significant figures of 0.624 moles of neon. Okay? Now you can look at sample problem 1.5 on page 58 in the textbook. You'll find the answer in the solutions, okay? But I'm giving you problems that aren't in the book so that you have a larger variety of things to look at. Now, our next thing up is molar mass. molar mass is the mass in grams of 1 mole of a substance. The molar mass of an element in grams is numerically the same as the atomic mass of that element in AMU. So 1 atom of carbon has an atomic mass of 12.011 AMUs. 1 mole of carbon then is going to have a mass of 12.011 grams. Guys, this means that we can read the periodic table 2 ways. We can read it in terms of AMUs for an individual atom. We can read it in terms of moles of that atom. Okay, the numerical value is the same, it's just the units are different. So 1 mole of carbon atoms has a mass of 12.011 grams. 1 atom of carbon has a mass of 12.011 AMUs. All right? So I can read the periodic table 2 ways. If you have grams of a sample of an element and we want to calculate moles of that element, then all we have to do is use the following relationship. Grams of A times 1 mole A of grams in 1 mole equals moles of A. Or we can look at the reverse. If I have moles of A, if I put grams in 1 mole over 1 mole of A, I get grams of A. So we're going to do a couple of problems, okay? Let me grab the periodic table here because I'm going to need it. Now I'm just going to make up problems so that we've got some stuff to work with. I do not have a periodic table with me. Well, I'll have to go with the ones that I know. Okay, let's say we were given 18.2 grams of sulfur. And I wanted to know how many moles of sulfur that was. If I look at the periodic table, 1 mole of sulfur has a mass of 32.066 grams of sulfur, okay, from the periodic table. So if I go 18.2 grams of sulfur, 1 conversion factor, I'm going to be in moles of sulfur. Now since I want to go 2 moles, the 1 mole of sulfur goes on top, the 32.066 grams of sulfur goes on bottom. So notice grams of sulfur divide out. So 18.2 divided by 32.066 gives me 0.568 moles of sulfur. Now let's look at a problem where we go the other direction. Let's say that we were given, let's go with 2.65 moles of carbon, and we're asked grams of carbon. Okay. Well, I know that 1 mole of carbon has a mass of 12.011 grams. So 2.65 moles of carbon want to end up in grams of carbon. So this time the grams is going to go on top. So 12.011 grams of carbon, 1 mole of carbon. So notice that moles of carbon divide out, and I'm going to take 2.65 times 12.011, and I get 31.8 grams of carbon. Okay? All right, guys, now I'm going to draw a picture for you. I'm going to put moles of the element in the middle. And I'm going to put grams of element over here. Put number of atoms over here. Moles sits in the middle, okay? It's kind of like Rome. Remember in ancient history, all roads lead to Rome? Well, in chemistry here, when we're dealing with the mole, okay, in our bookkeeping of chemistry, all roads lead to the mole. If you do not pass through the mole going somewhere, you've done something wrong. So if I want to go from grams to moles, or moles to grams, I'm going to use molar mass. If I'm going to go from moles of an element to atoms of that element, or atoms of that element to moles of that element, I am going to use Avogadro's number. Okay, you can think about these as like bridges. Okay, the molar mass bridge connects the island of moles of elements to the island of grams of elements. The Avogadro's number memorial bridge connects moles of elements to atoms of elements, atoms to moles. Okay? So, kind of sketch that out. It's something to have sitting there as you work problems. Looking at this now, you can see that you should be able to go from moles of one element all the way to grams of one element to numbers of atoms, or numbers of atoms all the way to grams of an element. So if you look in your notes, okay, I've kind of written this out for you. So if I've got grams of an element A, first thing I'm going to go to do is go to moles. So 1 mole of element A over the molar mass of element A. And then I'm going to use Avogadro's number, 6.022 times 10 to the 23 atoms over 1 mole, so I can get numbers of atoms. And I can go back the other way. Numbers of atoms, now I've got 1 mole on top, 6.022 times 10 to the 23 atoms on the bottom. Mass of 1 mole over 1 mole of element was going to give me grams of the element. Okay? So let's invent a problem. So a problem could say something like, how many grams of carbon would I need to measure out to have 8.2 times 10 to the 24 atoms of carbon. Okay? Now, we are asked grams, and we're given 8.2 times 10 to the 24 atoms. Okay, so I'm going from one end to the other. I'm going from numbers of atoms to grams. So I'm going to need a couple of things. Namely, I'm going to need 1 mole equals 6.022 times 10 to the 23 atoms of carbon. And I need the fact that 1 mole of carbon has a mass of 12.011 grams. Okay, so I'm going to start out with my 8.2 times 10 to the 24 atoms of carbon. I'm going to use 2 conversion factors, and I'm going to end up in grams of carbon. Now, let your units be your guide. I'm going from atoms, so the first place I go from atoms is moles. So I'm going to go 1 mole of carbon on top, 6.022 times 10 to the 23 atoms of carbon on bottom. So you can now see that atoms of carbon have divided out. I'm in moles of carbon. Now I can go from moles of carbon to grams of carbon. So I'm going to put the 1 mole of carbon on top, so it's on bottom, so it's opposite that moles of carbon, and 12.011 grams of carbon on top. So now notice that moles of carbon and moles of carbon divide out. I'm left in grams of carbon. So 8.2 exp24 divided by 6.022 exp23 times 12.011, and I am going to get 1.6 times 10 to the 2 grams of carbon. I wrote it in scientific notation so that we would have clarity about significant figures. I started out with 2 significant figures here. I have to end with 2 significant figures at the end of the problem. Okay? Now, let's look at a problem where we're going to go the other direction. Okay? Let's say we ask this question. How many atoms of chlorine are there in a 15.2 gram sample of chlorine? Okay, so we're asked number of atoms, and we're given that we are starting with 15.2 grams. So I need 2 things. I need the molar mass. 1 mole of chlorine has a mass of 35.45 grams. And 1 mole of chlorine contains 6.022 times 10 to the 23 atoms of chlorine. Okay? So I've got the numbers. Let me double check something here real quick. I need to get into the appendix here. Where's the appendix? Come on. Ah, there's what I'm looking for. Well, I'm gonna, yeah, I'll use that. Okay. Now, this time I'm gonna start out with the 15.2 grams. 2 conversion factors later, I'm gonna be in atoms of chlorine. So this time, I'm going to go from grams to moles first. So 1 mole of chlorine, 35.45 grams of chlorine. Grams of chlorine and grams of chlorine divide out. And now I want to go from moles to number of atoms. So I'm going to use 6.022 times 10 to the 23 atoms of chlorine on top. 1 mole of chlorine on bottom. So notice that moles of chlorine and moles of chlorine divide out. I'm now in units of atoms of chlorine. So 15.2 divided by 35.45 times 6.022 exp23. I get 2.58 times 10 to the 23 atoms of chlorine. 3 significant figures here, so 3 significant figures here. Okay? So we've done some problems. Now, we don't live in a world that only has atoms in it. We also have molecules. So we need to think about doing the same things for compounds, molecules, formula units, that we did for individual atoms. So that means we're going to move on to chapter 4. Okay, sections 9 through 11. Starts on page 179 in your textbook. So, let's talk about formulas for a minute. Empirical formula, molecular formula to begin with. Now let me remind you, an empirical formula is the smallest whole number ratio of atoms in a compound. So, ionic compounds and covalent compounds both have empirical formulas. A molecular formula is the actual number of each type of atom you would find in a molecule of a covalent compound. So when we talk about molecular formulas, we're only dealing with covalent compounds. An empirical formula could be related to an ionic compound or a covalent compound. Okay? So let's talk about empirical formula mass and molecular formula mass. The empirical formula mass is the sum of the atomic masses of all of the atoms listed in the empirical formula. Okay? The molecular mass, your book also calls it the formula mass, is the sum of the atomic masses of all the atoms listed in the molecular formula for a covalent compound. So let me give you some examples here. Okay? If I have sodium chloride, I've got 1 sodium atom and 1 chloride atom per formula unit. Or you could say in the empirical formula. So I'm going to have 1 times the atomic mass of sodium, which is 23.0 AMUs, according to the periodic table I'm using. And then I've got 1 chlorine at 35.45 AMUs. And all I'd do is I'd add those two together. 23 plus 35.45, that's 58.5 AMUs. Since this one only goes one place past the decimal, when I add them together, I can only go one place past the decimal. So 1 empirical formula, 1 formula unit for sodium chloride has a mass of 58.5 AMUs. Okay? Now, let's look at glucose. Its formula is C6H12O6. Now this is a molecular formula. Notice that it's got a common factor of 6 in there. Its empirical formula is H2O. So its molecular formula, C6H12O6. Okay? Its empirical formula mass would be 1 times 12.011 AMUs plus 2 times 1.0079 AMUs, these I have memorized, and 1 times 15.9994 AMUs. So 12.011 plus 2 times 1.0079 plus 15.9994 gives me 30.026 AMUs. So that's the empirical formula mass. Now, let's go for the molecular formula mass. Okay, it's going to be 6 times 12.011 grams. AMUs. And 2 times 12 times 1.0079 AMUs. And 6 times 15.9994 AMUs. So 6 times 12.011 plus 12 times 1.0079 plus 6 times 15.9994, and I get 180.157 AMUs. Okay, so glucose, being a covalent compound, has an empirical formula, it has a molecular formula, it has an empirical formula mass, it has a molecular formula mass. Now, there's a relationship between the empirical formula mass and the molecular mass. Namely, since I factored out a factor of 6 to go from molecular formula to empirical formula, if I just take the empirical formula mass and multiply it by 6, I'm going to get the molecular formula. Okay? Or you could also say if I took the molecular formula and divided it by 6, I get the empirical formula mass. Okay? So, empirical formula, molecular formula, empirical formula mass, molecular formula mass. Now, let's throw another new term in here, and that's molar mass. Notice it gets the pretty cursive-y, curly-Q-y type M as its symbol. It's a mass of 1 mole of a substance in grams. For a pure element, the molar mass is numerically the same as its atomic mass. We've already talked about that. So 1 atom of carbon has a mass of 12 AMUs. 1 mole of carbon has a mass of 12.011 grams. For a covalent compound, the molar mass is numerically the same as the molecular mass. So 1 molecule of carbon monoxide has a mass of 13.0189 AMUs. 1 mole of carbon monoxide has a mass of 13.0189 grams. For an ionic compound, the molar mass is numerically the same as the empirical formula mass. So 1 molecule of sodium chloride has a mass of 58.44 AMUs. 1 mole of sodium chloride would have a mass of 58.44 grams. Okay? Now, just like we did for elements, we can use mass as a way to count molecules. So let's think about the relationships. If I have a number of molecules, I can use Avogadro's number to get me to moles of that compound. You could also say number of formula units, because sodium chloride's only going to have formula units, no molecules. So I can use Avogadro's number to go to moles of the compound. Once I'm in moles of the compound, I can use molar mass to go to mass of the compound. Okay? So we're going to look at a few example problems. Now, again, we're just repeating the same pattern. We're doing the same thing for compounds that we did for elements. Okay? So, you can see something like, how many molecules of glucose are there in a 37.0 gram sample of glucose? Okay? So, we're asked number of glucose molecules. And we're given that we have 37.0 grams of it. So I need a couple of things. One, I need that 1 mole of glucose contains 6.022 times 10 to the 23 molecules of glucose. Tilt this a little bit just to make sure that I'm getting everything in. And I need the fact that 1 mole of glucose has a mass of 180 point, let's see, I'm going to roll this up here because I already have this one. Well, no, correct. Well, we'll just use 180 grams of glucose. It's close enough for my board work here. Okay? So, if we think about our islands, I'm going to go grams of glucose to moles of glucose to molecules of glucose. Now guys, when I'm solving problems, I like to write this out so I'm very clear on the steps that I'm going to follow. So this is going to require molar mass, and this is going to require Avogadro's number. So 37.0 grams of C6H12O6. My first step is to go to moles. So 1 mole of C6H12O6 for every 180 grams C6H12O6. Notice that grams of glucose divide out. I'm in moles of glucose. Now I can go to molecules. So 6.022 times 10 to the 23 molecules of glucose. 1 mole of glucose on the bottom. So now moles of glucose divide out. Okay, and I'm going to end up with an answer in molecules of glucose. So 37.0 divided by 180 times 6.022 exp23, and I get 1.24 times 10 to the 23 molecules of glucose. Okay? Guys, the devil is in the details here. It's really important that you take the time to set up the problem. You may want to write this out and then go gather the pieces of information that'll help you do these 2 steps. Each arrow represents a conversion that you're going to do. It represents a conversion factor that you're going to use in your problem. Okay, so be very kind of meticulous and write everything out. You're going to make mistakes if you skip steps and you try to do it in a hurry-up fashion. Take your time, write everything out. Okay, now let's try another one. Okay, so let's say that you're asked grams, let's see, yeah, let's go with grams of carbon monoxide given that you need 4.8 times 10 to the 24 molecules of carbon monoxide. Okay, so I'm going to be starting out with molecules of carbon monoxide. I know the first place that I have to go is moles of carbon monoxide, and then I can go to grams of carbon monoxide. Okay? To go from molecules to moles, I need Avogadro's number. 1 mole of carbon monoxide contains 6.022 times 10 to the 23 molecules of carbon monoxide. To go from moles of carbon monoxide to grams of carbon monoxide, I'm going to need molar mass. 1 mole of carbon monoxide has a mass of, let's see, 12.011 plus 15.9994. I have 28.01 grams of carbon monoxide. Okay? So if I start out with my 4.8 times 10 to the 24 molecules of carbon monoxide, 2 steps later, I should be able to be in grams of carbon monoxide. So 1 mole of carbon monoxide for every 6.022 times 10 to the 23 molecules of carbon monoxide. Molecules of carbon monoxide divide out, and then 28.01 grams of carbon monoxide for every 1 mole of carbon monoxide. Moles and moles of carbon monoxide divide out, so 4.8 EXP 24 divided by 6.022 EXP 23. When I say EXP, that means that I'm using the exponential notation button on my calculator, times 28.01. I'm going to need 223 grams of carbon monoxide. Okay? Now guys, doing that, realize that I made a typo in my notes. So I'm going to go back and fix this typo in my notes, and I want you to see where I fixed it. When I got the molar mass for carbon monoxide, I mistyped it. So let's fix this. 1 molecule of carbon monoxide has a mass of 28.01 AMUs, and 1 molecule of carbon monoxide should be 28.01 grams. Okay, let's save that. We can add more bridges to our island chain. Okay, but I'm gonna stop right here and give you a chance to let your brains cool off, recombobulate, and this is where we'll pick up in the next segment.